the next video on basic circuit analysis. Here we are going to solve problems related to the common emitter configuration of NPN transistor and a different aspect of load line analysis. Generally speaking, about any transistor circuit analysis, it is required to determine the collector current for various collected to emitter voltages. And one of those methods which can be used to plot the output characteristics to determine the output collector current at any desired collected to emitter voltage. However, a more convenient method, which is always known as the load line method, can be used to solve any such problems related to the output characteristics analysis of common emitter or any such configurations of NPN transistor. So now to perform the DC load line analysis, here we have considered a common emitter NPN configuration where the first circuit shows without any signal being applied. Therefore, the DC conditions that prevail in the circuit we are going to understand, and the output characteristics of the circuit is shown in the second figure. So now first let us start our analysis with the estimation of collector to emitter voltage VCE at any time can be given as VCE. So it is collector to emitter. So therefore you need to apply the KVL at the output collector loop. So therefore this becomes VCC minus ICRC. As we know that VCC is the supply voltage, which is a fixed value, and RC is also a fixed value. Therefore, it's just a simple equation where this simple first degree equation can be represented by a straight line method on the output characteristics. So this is known as the DC load line, that the straight line where to add this DC load line onto the output characteristics graph, we need two endpoints on the straight line. So that we will determine how to estimate these two endpoints for a common emitter configuration on the output characteristics analysis between VCE and IC. Now we consider that the collector current is 0. So when the collector current is 0, we know that the collector to emitter voltage is going to be maximum, because you can see here when the collector current is 0, which means it comes at this point. When the collector current is 0, you can see that the collector to emitter voltage is going to be maximum. So let us find how that is going to be maximum. So when the collector current IC is 0, you can find out what is the maximum VCE. Maximum VCE possible will be apply in the same equation whatever we have considered as VCC minus ICRC. When you are applying IC equal to 0 here, so therefore the maximum VCE possible will be equal to VCC. So this is what I have drawn here. I have kept the point as B point, which is VCC. So this gives our first point on the straight line, and this point B, which is VCC, is the maximum collector to emitter voltage. Now for the second point to understand, we set VCE equal to 0. So VC is 0, so this point. When VC is 0, what is the collector current? That is what we need to estimate. So what is the collector current? The collector current will be maximum actually. So let us find out how it is going to be maximum. So VCE, the equation we know it is VCC minus IC times RC. And VCE is 0. So we will substitute that. So this becomes VCC minus RC equal to 0. So therefore from this you can take the maximum IC point, which is equal to VCC by RC. So that point I have marked here as A. So this is the second point on the collector current axis. So now by joining these 2 points, you can see here that the DC load line AB is constructed. So why do we have to construct a load line? The resistance RC, which is connected to the device, is called as a load or the load resistance for the circuit. Therefore, the line we have just constructed is called as the load line. Now you can see here the current IC and the voltage VCE conditions in the transistor circuit are represented by some points on the output characteristics. The same information we are obtaining it from the load line. So thus when IC is maximum, which is when it becomes VCC by RC, your VCE will be 0. And when IC is 0, then your maximum VCE that is possible is equal to VCC. So for any other value of collector current, say OC, the collector to emitter voltage VCE becomes OD. So it follows therefore that the load line gives a far more convenient approach in the direct solution to the problem that we are encountering to obtain the operating points. So these IC and VC are known as the operating points or the zero signal values, which we call them as the Q point because it is the point on IC-VC characteristics when the transistor is silent, or we understand that when the transistor was applied without any signal, in the absence of signal. So that is why we call them as zero signal values of IC and VCE are the operating or the Q points for the transistor. So this estimation of Q points was a core objective for the output characteristics analysis. For that, we have taken a convenient method called DC load line. Okay, now we will try to take one problem related to the common emitter configuration, and we will understand the DC load line analysis by estimating the operating points or the Q points of the transistor.
Now let us solve one problem related to the DC load line analysis, or we have to find out the Q points or the operating points of the transistor. So now the question is, determine the Q point of the transistor circuit that is shown here. So here again we have considered the NPN transistor. Also, it is asked to draw the DC load line with beta equal to 180 and VB is equal to 0.7 volt. And you can observe from the figure that the given data are VBB is equal to 10 volts is given and VCC equal to 20 volts is given. RB, the base resistance, is 40 kilo ohms and RC is the collector resistance, which is given as 300 ohms. So now the presence of this RB, the base resistor, should not disturb us in applying the Kirchhoff's voltage law at the emitter side. Now, after applying Kirchhoff's voltage law at the base emitter side, we have VBB here. So we start at this end. So it will be VBB minus IBRB, the current through this RB base resistance. And then we will have VBE, the voltage drop across the base and emitter junction. So we will just write the equation as VBB minus IB times RB minus VBE equal to 0. So sum of all the voltages around the base emitter loop will be equal to 0. So now from this we can get the equation of IB, which will be IB equal to VBB minus VBE divided by RB. Now we have all the values where VBB is given as 10 volts, VBE is 0.7 and RB is 40 kilo ohms. So with this, we can find out what is the base current, which will be 232.5 microamps. So once you solve that, you'll be getting this current. And we know that IC, the collector current is going to be beta times IB. So therefore, beta is given as 180. So multiply 180 with IB, then we'll be getting IC as 41.85 milliamps. So to find out the Q point of the transistor, we actually estimate two different values. The first value that we have obtained is the collector current IC, and the next value that we have to determine is the collector to emitter voltage VCE, because for the output characteristics, we try to plot the graph between VCE and the collector current IC. So therefore, to get VCE, we have to apply the KVL again at the collector end. So that will give us VCC minus IC times RC. We know VCC is 20 volts minus RC. We have just estimated it as 41.85 milliamps into RC, that is given as 300 ohms. So therefore, upon solving, we'll be getting VCE equal to 7.445 volts. So you can just round it off to as 7.4 volts. So finally, the Q points are. Now we have obtained the operating points, and that I have plotted in the output characteristics of the NPN transistor. For a common emitter configuration, the output characteristics will be plotted with respect to the collector to emitter voltage, output voltage versus the output collector current. And we have got these points, which are the operating points required for the transistor. Now, to draw the DC load line, we need to determine what is A point and B point. So, which means for the straight line to be drawn, we require 2 points. So, first we find out, as per the theory we have discussed, we know how to calculate the maximum VC. So, maximum VCE is equal to VCC. And this is possible. This will be equal to VCC is given as 20 volts, and this is possible when IC is equal to 0. So this is the first maximum value. And then maximum IC, the formula is VCC by RC. We know what is VCC. VCC is 20 volt. RC is 300 ohms. So this will give us an IC of 66.6 milliamps. So this is possible. Maximum IC is possible when VCE equal to 0. So these are the 2 points. So IC is 0. So at that point, maximum VCE possible is 20 volts. And therefore, when VC is 0, the maximum IC, the collector current that is possible is 66.6 milliamps. So this will be 0, minimum value. Hope this video would have been useful for you to understand how a DC load line analysis is performed to determine the Q point or the operating points of an NPN transistor in a common emitter configuration. So meet you all in another video. Until then, stay safe. Thanks for watching this video through Electronics Insight channel.